There we go. Screen share. Hi, Sydney. I know there are emails from you. I'll respond to them eventually. The one about the exam, don't worry, you did everything perfect. So good job. Oh, good. I do have students. Keaton's going to be here, right? He never misses calculus. Wow, that went really fast. Let me see if I can do that again. Not as good. I imagine April will be here. Yeah, it was definitely in degree mode. Yeah, I saw that and I'm like, I think I know what the issue was there. So, all right. I got 1 minute. Wow, what's that drink? It's what? Just a seltzer? No. Celsius. How much caffeine does that have?
275.
That sounds like a lot. Like a Mountain Dew has like 30, right? So you're gonna be awake for a while. Yeah. Gotta be a little careful with that stuff though. I mean, I once overdid it myself. I had to finish my thesis. I had a week to do it. So every day, 2 or 3 5-hour energies. It was a bad idea. I got it done, but I was exhausted. Absolutely just done. I didn't realize that at the time, but my advisor gave crazy thesis problems. So I did it and I was like, gosh, no, Professor Miller, I've only got 130 pages of math. You think I could have a PhD now? And he's like, okay, yeah, sure. That was it. That was crazy, man. Wow. Welcome back to class, everyone. I graded the exams. It was actually very, very good overall. Great work. If you didn't do so well, remember I do allow for corrections, so those are available to you. Just write the corrections on a separate sheet of paper, and I will I will I can award back some points. Okay. Any questions before we get rolling today? We're missing some people. We're missing Connor. I think Connor might have an athletic event though. I could be wrong. Maybe not. Maybe you don't know. You don't know where he went. Okay. Oh, he hurt his elbow. All right. I My girlfriend, now wife, and I once took a class together, and it was an intro to psychology course. And I was trying to do a lot of things. I was trying to study for grad school. I was trying to do just too many things, and I would occasionally skip class. You shouldn't do what I did. I was skipping it to do homework, no less. Uh, and then no, because I'd pay attention in class. But I always felt bad for my girlfriend, now wife, because the professor would be like, "So where's Brandon?" And she'd be like, "Oh, I don't know." No. No, don't do your homework in class. Not unless you really, no, don't do it. Don't do it in class. Okay. All right. Well, welcome back to class, everyone. We're going to finish up graph sketching today. So if you're tired of sketching graphs, this is the last time we'll do it in class. You do have a homework on it. It is kind of a longish homework. So do the best you can. A lot of this sort of work is, it's not particularly deep sometimes, but it's worth learning to do. And after we're done with this graph sketching part, we're going to move on to a topic called optimization. And this is actually a really important topic in our world today, especially in computer science, where optimization is used in artificial intelligence. Whether you realize that or not, these ideas in calculus are actually pretty important for understanding AI today. Like at one point, maybe 10 years ago, I'd say calculus is most important in the world today for physics. And now I'm like, calculus may be most important in the world today for AI. Like that's where I'm starting to lean. Like our world is changing. Okay, so let's just recap how we plot things. Uh, Here we were working on this problem, part B. H of x is equal to x over 2 minus sine of x. And we're simply going to plot this function over the interval from 0 to 2 pi. If you're wondering how do we do that, I gave some steps here on the handout, some basic steps we follow. Basically, we find the critical points, we find where the function is increasing or decreasing, we find the local extrema, we then find second order critical points, the intervals of concavity, any inflection points, and we'll go from there. So last class, we had begun computing where our function h was decreasing and increasing, and then I ran out of time. So let's continue with that. We're going to find where this function is increasing, decreasing. So what have we got here? Well, let's just recap. We took a derivative, right? So our original function is this x over 2 minus sine x right there. And we took the derivative, we got 1/2 minus cosine x. We figured out that this means we want to find x for which cosine of x is 1/2, and then we use the unit circle, remember that? And we found that it had critical points at pi over 3 and 5 pi over 3. That's what formed these intervals. And then we plugged in for test values, and now finally we're ready to write down what behavior was, right? So negative means decreasing, increasing, decreasing. Okay, and I guess I probably could have finished class by writing that. That wouldn't have taken too long. But let's move on to the second derivative. Second derivative. What's the second derivative going to be here? Almost. It is positive sine x, yeah. Sine x. So we want to figure out when this is equal to 0. Does anyone know, when does sine equal 0 off the top of your head? Nope. 0 is one of them. Sine of 0 is 0. Pi. Pi is the other one. It's 0 pi and technically 2 pi as well. If I were to pull up the unit circle here, and let's do that real quick. I don't have a web browser open. All right, let me just put up a web browser. I usually have one open. Usually with math. Usually with math in it. Oh, there we go. Nice little picture of a unit circle. Sine is the y coordinate, right? And so we can see it's the y coordinate is 0 here at 0 radians or 0 degrees. And the other place where the y coordinate is 0 is right there at pi or 180 degrees. And then technically also, even it'd be at 2 pi as well, because you circle back and our interval technically includes 2 pi. Remember the interval we're plotting over here is 0 to 2 pi. Okay. All right, so those are sort of our second order critical points. And now we're able to make intervals. Our first interval is going to be from 0 to pi. And our second interval will be from pi to 2 pi. Technically, this is interesting because it's telling us that right at x equals 0 and right at x equals 2 pi, the second derivative is 0. So technically, we don't need to, before I would include the endpoints here, but because the second derivative is 0 there, I can't really do that at this point. And now I just need to plug in some test values and I can figure out the concavity here. All right, so what's a good test value to plug in? 1. I'm going to do pi over 2 because I like that one. Because I remember what sine of pi over 2 is off the top of my head. It's 1. And if you were me, what would your test value be here? Close. 3 pi over 2. And do you know what sine of 3 pi over 2 is? There's 3 pi over 2. It's -1, yeah. Someday, I hope you will have this completely memorized. And so it's concave up and then concave down. That doesn't look like a D. Concave down. All right, so this is very good. We've been able to figure out where the function is increasing and decreasing, where it's concave up and concave down. There are two things I've kind of neglected though. I need to figure out where the local extrema are and where the inflection points are. I kind of went out of order here. So we expect there to be a local max, right? Or perhaps a local min. Looking at this table, where's our local max going to be at? Five pi over 3, correct. Yeah, because at 5 pi over 3, we go from increasing to decreasing. So local max is at 5 pi over 3. And where do you think the local min is? Pi over 3 right there. Yeah, because we go from decreasing to increasing. All right. And do we have any inflection points here? Yeah, looks for an inflection point at x equals pi. Well, no, it's not liking me too much here. X equals pi. Okay. And so we know where these points are. Now, of course, it's really helpful for us to know also the y coordinates for these points. And so to evaluate those, we have to go back and look at what our h is. In our case, our h is ugly. It's ugly. So I'm going to put it in on Desmos, which okay, I'll admit you're like, Brandon, you're using Desmos to graph by hand. Isn't that kind of, I don't know, hypocritical? Yeah, I'm just using it as a calculator though here. I'm not going to plot anything. Well, it'll plot things just because it forces me to plot things. But here, I'm going to turn it. I'm going to turn it off there. See, now we don't know. I guess I should call this H there. Okay. All right. So now we can't see it. Sine of X. All right. And now what I want to do is plug in my critical points back into here. You could evaluate this using the unit circle and all of that, but I'm going to just do 5 pi over 3 here. I get 3.484. So kind of on the side here somewhere. I'll do it in orange. h of 5 pi over 3 is 3 point, was it 484? Yeah, that's what it was, 484. And now I'll plug in for pi over 3 to see what that's going to be. Negative 0.342. Okay, that looks good. And now I'm going to want to do the same thing for pi here. What's h of pi going to be? I plug in pi. 1.571 when I round. Okay. And for this problem, this is basically all I need to plot my function, which is nice. So let's begin by plotting our local maxes and local mins. So 5 pi over 3, where on earth is that here on my number line? I mean, there's 3 pi over 2 here. Where is 5 pi over 3? I guess maybe I should have split it up into thirds as well as halves. So in my mind, like pi over 3 is about here. Maybe more like right there. That's where pi over 3 is. And so that's what I kind of expect there. So yeah, let me just kind of, yeah, I don't, maybe right there, right there. All right, and so here in my coordinates, this is about negative 0.5 right there. And so if I'm going to plot this local min, I'm going to need the y coordinate to be at about negative 0.342. I think it'll go right about there. That look good to you? And 5 pi over 3, I think that's going to be right about here. And that's going to have a value of about 3.484. So way up here, really almost practically at the top right there. It auto-filled it into a hexagon for me. Did you see that? It made a little, OneNote will do that. It made it into a tiny, my squiggle looked too much like a hexagon. Well, it didn't there. Okay. All right, so you see how those got plotted there? It's a little clunky, but we can do it. And then there's an inflection point, right? Around 1.57 at pi. So 1.57. Yeah, let's make this purple now. That's about it there. All right, that looks pretty good. And now let's think about what we want. We want to plot where this is concave up and concave down. I like to use orange for concave down and green for concave up. So concave up is from 0 to pi. There we go. So green is concave up. Orange is concave down. All right. So do you remember what a concave up shape looks like? Smiley, yeah. Smile like that. Now, if I go back and I look at my increasing, decreasing here, I can see that I need it to be decreasing just to the left of pi over 3. And then after that, it's going to be increasing. And so if I wanted to imagine how my function might look, it'd be going down, and then on this interval, it'll be going up, and then on that interval, it'll be going down. And now I just got to match the concavity and everything with it. So it'll probably look something roughly like this. I mean, I'm a little bit of guesswork here. That's a nice concave up shape, I think. Now you might be wondering, how did I know to start right there? Any ideas on how you could figure out where to start? On the left when you have one of these closed intervals? You can plug in 0 into H, right? Yeah, if you plug 0 into H, you know what you'll get? 0, yeah. What happens at 2 pi? What happens if you plug 2 pi into H? You get pi minus sine of 2 pi, right? What's sine of 2 pi? Yeah, here, let's write this one out. So we'll get 2 pi over 2 minus sine of 2 pi. 2 pi divided by 2, I know that's just pi. What's sine of 2 pi? Zero, yeah. All right, so it's gonna be about pi here, which is maybe right about there. By the way, we have some Pi Day celebrations coming up after break on Pi Day. Sigma Zeta is doing something. They wanted me to make up some math problems for them to share with people in the campus center. I'll try to make them interesting and doable. That's hard to do. All right. And so that gives us a good shape because we know this has to be concave down. And so when we plot it, it should roughly look like that. And this is how people had to plot functions back in olden times. I know this is kind of like a field trip to like, the horse barn up the hill. We're gonna be like, so how did we make our horses, roadworthy? Yeah, it is kind of like that, but it's good for you nonetheless. Okay, so that's this problem here. Now I want you to at least try out the last problem on our sheet. This one is more involved. Part B right here. Try it out, do what you can, and we'll discuss it. I was talking with Monica Lewis on the way back from chapel, telling her about coronal mass ejections. Oh, I was right. It was around 1860. Do any of you know about the Carrington event? No. There's a giant sunspot on the sun right now. And that usually is followed by what's called a coronal mass ejection, where basically a huge amount of radiation gets ejected by the sun in like a stream. And in 1859, it hit the earth. We had a direct impact and it fried all the telegraph wires at the time. It just destroyed all, and there weren't that many telegraph wires in 1859. And there wasn't, most people did not have electricity. I don't even think there was running electricity for most people. Well, I know it wasn't, it wasn't for most people, but there was a lot of them. But yeah, the weather right now is there's a geomagnetic storm coming. There's a giant sunspot on the sun. And yeah, that's it. It can temporarily disrupt the Earth's magnetic sphere too, which is kind of dangerous because the Earth's magnetic sphere is what prevents us from getting radiated. So yeah. Yeah, it does sound a little scary. Maybe I shouldn't be telling you youngsters about it. You're gonna like go back to your dorm room and be like, it's time to build a Faraday cage. A Faraday cage will keep your electronics safe. Yeah. Yeah, yeah, sorry. I have a doomsday element, the interest in that sort of thing. It's not always good. The problem is I can deal with, disastrous things like that without getting too worked up, but not everyone can. I can remember when the pandemic first started and we hardly knew anything about it. And so I did a differential equation model to find out how long the pandemic would last. This is like back in March. And I was like, all right, how long is this gonna last? And I was like, wow, like a year to 2 years. That's how long it would be. And that was accurate, right? And I even did a fatality estimate, and it was pretty accurate too in the end. Yeah. Very scary stuff. Uh, I remember just having that and being like, oh no. Oh no, this is not gonna be good. This is not good. Incredibly bad. Yeah. So if you're wondering, how do I take the derivative of G? I'm gonna do it here. You can check your work. There, there should be, I believe, 3 critical points. No, two. There are there are 2 critical points, sorry. And both of them occur because the denominator is 0. All right. Oh, I forgot I was pausing my share here. Let me show it. Online students here. Resume share. Yeah, there we go. Let me unfreeze. There we go. All right, so I did the quotient rule here. Oh, this one's awful, huh? Get that. All right. Don't you just wish you could cancel things? Part of you is like, this must be cancelable, right? Because it's got like this x squared and the 16, and there's an x squared and a 16, but you cannot cancel things. Well, close. It'd be +4 and -4. Because when you square 4, then you get 16. So x squared plus 16, can this x squared plus 16 here, can this ever equal 0? No. If you set this equal to 0 and solve for x, you will get an imaginary number. And we don't like those. And so the critical points can only occur when the denominator is 0. And when is the denominator 0? Negative, yeah, -4 and 4. All right, now you can make yourself a lovely table. Plot it. Oh, by the way, I forgot the first step, and the first step is actually pretty important. What are the vertical asymptotes of this function? Just looking at this quotient here. Yeah, -4 and 4. Yeah, the vertical asymptotes are there. Yeah, because when we plug in, for instance, x equals 4, we'll get 0 in the denominator and not 0 in the numerator. Sometimes, yeah, sometimes the vertical asymptotes will correspond to the critical points. Not always. In practice, it'll always happen when yeah, it's when the denominator equals 0 and the numerator is not 0. Okay, so we got some information here, right? We got these critical points, -4 and 4. Now the hard part is taking the second derivative. Go ahead and try that out, or make the table for increasing, decreasing, and find local maxes and local mins. Though I don't think there are going to be any local maxes or local mins on this one. Oh, wow, that's a fancy calculator. Look at that. Can it do anything?
Seen that before. I think you can run like Python scripts.
You can run a Python on it? Oh, it's in Chinese. I can't read that. Wow. Everything can run Python now, like a Raspberry Pi can run it. It can? Ah, wow. Yeah, it still runs on BASIC, I think, a version of BASIC, which was like the beginner language I had to learn on. QBasic in particular. It was a great language to learn on. Not many people realize this, but Microsoft's first major product was the BASIC programming language for personal computers. That was their first major product. And then they branched into other things besides BASIC. All right. There's my G prime. I'll have to work that out eventually. G double prime. There we go. All right, I didn't do the whole second derivative, just part of it. You do the rest. How's it going, online students? I'll admit, this isn't the most exciting type of problem. This is, me personally, this type of problem does not get me excited. But it is part of the curriculum, so I teach it. Yeah, that's it. It's scary, isn't it? I recommend factoring out something and canceling something. Yeah, it's bad. How's it going?
Yeah, wrong.
Yeah, I think you did. Let's take a look here. So if you plug 0, you plug -15. Oh wait, no, that might be. Let me look. No, you're doing it right. Keep going. Yeah, that's perfect.
So the local math.
There isn't one. So for your intervals, did anyone figure out what happens for the first derivative? Our intervals are going to be what? -infinity to -4, -4 to 4, and 4 to infinity, right? I'm not going to show the work here, but what did you find for the first interval? Was it increasing or decreasing? Anyone want to share? It is increasing. Oh, I'm afraid not. It is not increasing. Here, let's do it together. What happens if I plug in -5 into the derivative? Well, yeah, what'll happen is the -5, when you square it, will give you +25. And so you'll have +25 in the numerator plus 16, which will give you +41 here inside this yellow portion. And there's a negative in front, right? So it's a -41. So I'll get a -41 in the numerator. And in the denominator, when I plug in -5, I'll have 25 minus 16. 25 minus 16 is 9. 9 squared is 81. And so this will be negative. I guess these are test values now, actually. Looks like I am doing the test values after all. All right, test vals. Right. So it'll be decreasing here. All right, what happens on the interval from -4 to 4? What's a good test value to use? Even better, 0. 0 is on that interval from -4 to 4. And what do we get, a positive number or a negative number here when we plug in 0? Negative. Yeah, it's weird. We're going to have a -16 in the numerator. And in the denominator, we'll have 16 squared. And all the computer scientists know what that is off the top of their head, right? It's 256. It's 2 to the 8. Okay, you're first year computer science students. You don't have it memorized yet. But eventually you'll have 2, 4, 8, 16, 32, 64, 128, 256. 512, 1024, 2048, 4096. I don't know what it is after that. All right, then we'll plug in 5 and for the next test value, and that too is gonna be, it is decreasing everywhere. Very weird function. Just decrease, decrease, decrease. Everywhere we go. All right. So those are our increasing functions there. Okay. Now let's talk about the second derivative. The evil second derivative. So here I started doing the derivative and then I stopped. I did low right there. And then the derivative of high, negative 2x, minus high, right there, negative x squared minus 16, times the derivative of low. So what's the derivative of low going to be here? Close. Times 2x, yeah. So you'll have the 2, and then in parentheses, x squared minus 16 to the 1, but I don't bother writing the 1, times the derivative of the inside. Now this looks just awful, doesn't it? And unfortunately, you have to find the second order critical points. So does anyone remember, what is our trick to doing that? How do we, yeah, well, we could solve for x, but there's a dumber way to proceed first. There's something special we could do. There's an x squared minus 16, an x squared minus 16, an x squared minus 16. What's that just sort of screaming at you to do? Factor it out and cancel, right, right. Right, so we've got to factor out, well, first of all, let's point out what the denominator simplifies to. That simplifies to x squared minus 16 to the 4th. How many x squared minus 16s can I factor out of the numerator? Unfortunately, just one. There are 2 copies here in the term 1, right? In term 1, this is what I call term 1. What I call term 2. Oh, term 2 is huge, huh? All right. Term 1 has 2 copies of x squared minus 16, but term 2 only has 1 copy. And so I can only take 1 copy out of both. And so if I do that, I'll get x squared minus 16 here, negative 2x minus, and I'll still have that negative x squared minus 16. I'll have a 2 and a 2x. Oh man, there we go. All right, I'll let you take it from there. It's not going to be pretty, but we can do it. I believe in you. How goes the deadly algebra here? You're good. Yeah, now you just got to multiply everything through in all its horror. Don't you remember the good old days back when we were doing the quadratic formula? Those were good times. Last semester at this time, it was all quadratic formula. And maybe a little bit of trick, just a tiny amount. So the nice thing is I can cancel out the x squared minus 16 with one of the x squared minus 16s in the denominator. And I'll be left with a cube. The only terrible thing is I'm left with this thing in square brackets. And we have no choice. We must multiply it all out and hope for the best. I think the hardest part at this point is dealing with the negatives. So what I've done here is I multiplied out the part in yellow. And this is what I got. And then yeah, I'll get to it eventually. And then I can multiply out the green part, but I want to make sure when I multiply it out, I put it in like parentheses or brackets or something. So I don't mess up the negatives. So negative x squared times 2x should give me negative 4x cubed. And negative 16 times 2x should give me negative 64x. And now I'll try to distribute that negative and see what happens. So I'll still have this negative 2x cubed plus 32x, and then I'll have a 4x cubed plus 64x. And now I have negative 2x cubed plus 4x cubed. That'll be 2x cubed plus 32 plus 64. I think that's 96, right? 96x. Yeah. And is there anything we could do to simplify this numerator? Yeah, we can factor something out. Megan already mentioned one that we can factor out a 2. There's one other thing we can factor out, an x, yeah. And so we'll have come on, erase. There we go. X squared. 96 divided by 2. My goodness, what's that? I believe that's 48. Huh. See, it does simplify and it looks nice and compact, but man, it takes a while to get there, huh? Derivatives are not easy, but there we go. But that's the second derivative right there. All right, so what are the second order critical points here? When is this thing equal to 0 or is it undefined? When does that happen? 4 and negative 4, definitely. There is one other new point though. That numerator can now equal 0 somehow. 0, yeah. Negative 4, 4, and 0. The x squared plus 48 term, that can never be 0. If you set that equal to 0 and solve for x, you'll get an imaginary number. So definitely not 0 there. But yeah, that's the idea here. We get negative 4, 0, and 4, which means we now have the privilege of having a table with 4 intervals. We could do it. Well, I don't know. Can we do it in 15 minutes? Maybe. I'll push us along if we need it. You're like, so much typing in, huh? Would you like me to expedite your mundane computations here? Yeah, let's do that. I'm gonna do it all mentally again now. I prefer that method, I guess. I'll get a negative, I'm plugging in -5 for this first interval, okay? So I'll give me a -10 here. Oh, I guess I just picked, yeah, -1 and 1. That makes more sense, yeah. Yeah, easier to compute. I don't know, I just picked something right in the middle. Sometimes I'm like, that always seems like the best option to me, but maybe it's not. All right. So inside this parentheses, I know -5 squared is 25 plus 48. That'll bring me up to 73. And so, and the numerator, when I plug in -5, will give me -10. So I'll get a -730 over whatever 25 minus 16 is. That's going to be 9 cubed. Does anyone know what 9 cubed is off the top of their head? I believe it's 700 something. 9 times 729. Right. -730 over 729. Oh, that was fun. All right. Now I'll try to display my mental arithmetic skills again here. I believe I'm going to get -98 over what? What was this going to be? Ooh, oh, this one's interesting. I'll have a -98, but it'll be a 1 minus 16. It'll be a -15 cubed. And I don't know what -15 cubed is off the top of my head. Well, oh, yeah, no, because it'll be a positive when you cube it. Yeah, -3,300. Oh, that's awful. But the important thing to see is that it's actually a positive number because negative. It's positive. Be shame if, it'd be nice if the world worked that way, right? Negative times a negative is positive, but two wrongs don't make a right. Trying to move my intervals down a little bit, and OneNote is not being cooperative. Oh, it's actually freaking out a lot. See, this is why I should ditch Microsoft. Because it just doesn't work for me. They were fine when they were making BASIC in the 80s, but all right. This one is going to be 98 over -3,375, which is negative. And when I do +5 here, I'm going to get +730 over this would be 729 positive there. So the concavity is interesting. It flips a lot. It goes down, up, down, up. The function's decreasing everywhere, right? But the concavity is flipping all over the place. All right. So we've done all that. Any inflection points? It seems like -4 is an inflection point, but it's not, and neither is 4 because there's vertical asymptotes there. 0. All right. We got an inflection point at x equals 0. That's it. That's the only special point we get. No local maxes, no local mins, nothing. Just a lousy old inflection point. By the way, these are the hardest types of problems I ever give, okay? They're awful. I'll make sure to post this on YouTube promptly in case you're like, how do we do this again? It is involved. All right, now the last step, and at this point it'd be good to just kind of recall what our function is. Our last step is to find the limits as x goes to infinity. And so let's do that. So there's our g of x, and I'll take the limit as x goes to positive infinity of my g of x here. And in fact, it's going to be pretty similar to what I get when I go to negative infinity. So just to recap, I'm basically going to identify my leading x coefficient here. This is my an x to the n, and then this here is what I would call my bm x to the m. And the idea is you take the coefficients. So what's the coefficient of my x here? 1. Coefficient of my x squared, also 1. And then you take the limit as x goes to infinity of x to the n. Now in this case, my n is 1 minus my m. So I'll have a 1 minus 2. And so I'll be taking the limit as x goes to infinity of x to the negative 1. Does anyone remember what that equals? 0, yes. And it's the exact same thing if you do x to negative infinity. I won't write out all the details, but it too will equal 0. And so from this, what is our horizontal asymptote? All right, you're like, hold on, wait, what do you mean horizontal asymptotes? I thought we were taking limits. So as x grows larger and larger, what do my y coordinates approach? 0, yeah. That's a horizontal asymptote at 0. All right. Okay, everyone, we're about ready to plot this. So technically, I should, if I'm being a gentleman, put a little dashed line here, but I'm never really going to see it. Putting a dashed line on the x-axis right now. There we go. Try to make it so you can see a little bit. That looks nice. All right, so I need to draw a plot somehow that's going to be, it's going to be decreasing everywhere. So it's just going to be this decreasing function. And my concavity is going to be flipping all over the place, right? Concave down from negative infinity to -4 and 0 to 4. So I'll draw a little line here just to remind, this is concave down, and then concave up here, and concave up here. All right, see if you can figure out what on earth this thing, oh, and we have an inflection point. Where's our inflection point at? It's at 0. What happens if I plug 0 into my original function here? What will I get out? 0. Okay, inflection point right there. All right, try your best to identify what this crazy looking function is. This is the boss level. Okay. Oh, I have a meeting in person today? Oh. I think this is one of the meanest problems of them all. Try it out though. Or you could just plot it, Megan. And hope I don't notice. Okay. I saw that look on your face. You were like, how on earth am I supposed to get? Now imagine it's an exam. So I'll tell you what I'll do on exams. I'll say, here's a function, but I won't tell you what the function is. I'll say, but it's increasing, decreasing on these intervals, concave up, concave down on these intervals. It has these asymptotes. Go ahead and plot it. So yeah, a graphing calculator will be of no use to you. You'll unfortunately have to use your brain. All right. So the key is to remember our shapes, right? We have concave, I wanted that in blue. Concave up. See, OneNote's weird. Like you can see how I selected the blue there and it didn't register yet. It takes a while. All right, concave up, concave down. Now I need decreasing for all of these. So my decreasing shape for concave up is going to look like that. And my decreasing shape for, well, this is actually not entirely concave down, but OneNote's giving me such a fit right now. I don't want to bother fixing it. So I need concave up decreasing shape. So let's look here on this interval from -4 to -2. On this interval, I need a concave up function. It needs to go through this point here, and it needs to be decreasing. And so I'm going to have this concave up shape that's decreasing right there. Does that make sense? All right. What do you think is going to happen on this orange interval from 0 to 4? Yes, it's going to zip down like that. There we go. That's the easy part. Now we got to figure out what concave up and concave down are like over here. So here I've got green, right? So I'm going to need this shape here, this decreasing concave up shape. Where should it be located? In this section here or this section here? The top or the bottom? The top, yeah. Because I need it to grow close to 0, right? Because there's that horizontal asymptote there. And so the shape I'm going to get is really weird. It's going to look like that. Basically, vertical asymptotes allow you to have these giant gaps where it's like, on one hand, it's like going down, down, down to negative infinity, and then suddenly it flips over here. And how about this one? Are we going to go up here or down there? It's on the bottom, yeah. And it too will approach its asymptote. And that's it. That's the plot of this thing. Whew. This is hard. This is hard, and we have only 4 minutes left. So I think I'm just going to end class early because I put you through so much stress. And if I started talking about optimization now, I'm pretty sure you wouldn't remember anything. So next class, we will start optimization. All right, online students, any questions before I hang up? Nope, you're all set. Good work on the exam, both of you. Good jobs. Actually, everybody did pretty well. Good work. All right, bye.